Okay, let me get started. First question, I guess, is are there any questions about the project? The project is due, progress report is due at midnight tonight. Am I correct? And and again, you guys should know the drill now. Um, no more than 5 pages total size. Um, and again, what do I want to learn from this? I'm hoping that we will have seen that you have done something and made some progress since the proposal, and that you have a clear idea of what you want to do to finish up. That's kind of, I guess, the main goal that I want to see here. Any questions? Okay. The I will also probably, hopefully, I'll remember to say this again at the end, but tonight, by midnight, you'll turn in the progress report. The hope is by relatively early on Friday, you will get back the list of the 3 projects you're supposed to review, the reports you're supposed to review, and we're going to need that done by Sunday night. So expect to have that level of reading to do. Um, we the TAs are also going to be looking at the comments from the progress, from the proposal and the progress report to make sure, so to identify which students gave, you know, helpful, substantive feedback and distinguish that from people who may have done a fairly casual job. So try to do what try to be helpful when you read the proposal, when you read the progress reports. Um, and that's my and reasonably serious with this. Okay. In general, I think that the scores were pretty consistent last time, so that was a sign that the reviews were, uh, kind of the scores meant something. But I want to make sure the comments are helpful to people who are going to be dealing with the reports. Okay. Any questions about progress reports? Before I go any further. Okay, today I'd like to talk about one of my, kind of, favorite methods or things to do in data science, which involves nearest neighbor methods. Um, Nearest neighbor, we've talked the last couple of classes about, classification methods like logistic regression, where you train models to try to give a label for a particular point. Um, Nearest neighbor methods are a very good way and nice and in some sense simple way to do classification. What is the idea? The idea is that if you take every point in your training set, if every point in your training set has a label, here we have red and blue are the 2 classes that we have. We can, if this is a two-dimensional feature space, again, the way to think about it. In this particular example, we've got two dimensions of feature space, F1 and F2. And we would like to basically carve up feature space into regions that are points that are within it are going to get assigned red or are going to get assigned blue. The nearest neighbor classification method basically takes and there are variants and there are subtleties to it, but the basic principle is given any particular point in space, let's say that one, we identify what is the nearest point to it, okay, which happens to be this, and give it the same label, this unknown point X, give it the same label as the nearest neighbor. So if we have in the training set examples of blue and red things or men and women, okay, if this was in height, this could have been, men and women in height, weight, space, okay. Um, you find which training point is closest to you and, use that to give you the label. There's several good things about the idea of nearest neighbor classification. One is, it is very simple. Okay, so the idea of saying, look through all the um, examples, find which one is closest to to the target that, to the new input that you want to label. Okay, that is conceptually a simple thing. That is one for loop in some sense. Nearest neighbor methods have the advantage that they are very interpretable. When you look at the decision afterwards and said, why did you say that point was red? That point was red because you can point to which was the example that was closest to it. Okay, and that was, and that kind of gives you a conviction that the nearest point is red. And the other thing is that it gives you the ability to have nonlinear decision boundaries. Last class we talked about logistic regression. With logistic regression, if we were carving this thing up into, red-blue space, we would have presumably drawn some kind of a line like this, and everything below this was going to be red, blue, and everything above that was going to be red. With nearest neighbor boundaries, you can get very, very crinkly boundaries. There's no reason why it's going to be a straight line. It can be a very, very complex decision boundary. And this is an important thing. So these are the reasons I like nearest neighbor. Basically the reasons I like nearest neighbor stuff. I like that I understand it. I like that if I wonder why did this guy get a label, I can see it in the, I can see it in the, look at the nearest neighbors and understand it better. And you get the performance of nonlinear methods, okay, which is good. The other thing is that I just think nearest neighbors are a very, very useful thing to do for visualization. Okay, so if I want to understand something that my data set is telling me, I always find that nearest neighbors are identifying what the nearest neighbors are. That gives me a good idea how well the feature space is capturing the domain that I wanted to know. So, I wanted to kind of give you an example that came up in a project that we were working on. My lab does work in graph embeddings, which are ways of taking networks and reducing them to low-dimensional feature spaces to serve as low-dimensional vectors to serve as features for machine learning models. And we had two different algorithms, and we wanted to decide which one was better. And of course, you could take the features and run them through some test on an application. But another way to assess whether one method was better than another was to take a graph that we sort of understood. Okay, and in this case, I'm going to talk about the graph. We did this analysis on the graph of websites. The web, if you think about it, is a graph. Every web page is connected to some other web pages. You can imagine that every web domain is connected to every other web domain based on links from the site. Okay? If our feature vector for representing the nodes was good, the nodes are going to be the web domains. Okay? And we would expect that similar domains are going to be mapped to similar points. That's kind of what we would want from our feature representation. So what do I do here? I have two different algorithms for for building feature representations, DeepWalk and RandRA. Okay, which one of them is better? Okay, and I want you to take a look and you to tell me. Okay, what are we doing? This shows one of the websites was stonybrook.edu. And this is showing after we had converted, the entire graph to these feature representations, which were the 10 closest websites to stonybrook.edu in this feature space. Okay? Which one of these is better? And again, this now is somewhat of a qualitative thing, but which one is better? Does anyone have a feeling? Okay, in TV land, you probably can't read these numbers off the screen, so you may want to go back to the original slide. I guess looking for the closest neighbors to Stony Brook in Deep Walk space was Binghamton, CUNY, Lehman College, which is part of CUNY, Barnard, which is a branch of Columbia University, ESF, which God knows what that is. Actually, maybe like Empire State Foundation or something like that. I'm not sure what that is. Baruch College, which is in the city. Okay, Colgate, Hunter College in the city, Hamilton College. Randeni was also connected to some things. It was Duquesne University, Wellesley College, University of Illinois, Amherst, Massachusetts, Ohio, Binghamton, Smith College, okay, Vanderbilt. Which one does a better job? Does anyone have a feeling? What? You like Randeni, and why do you like Randeni?
The class of the university that near to Stony Brook, Deep Walk, we have some colleges.
Okay, you're saying you're seeing colleges, okay? Like you want to say Barnard and Lehman and Colgate are colleges. Of course, McAllister is a college, and Smith is a college, and Amherst is actually a college, okay? So I'm not completely sure I agree with that. But again, it's okay to have an opinion. Did anyone have a different opinion? Okay. What?
I think the Deep Walk.
You think the Deep Walk one. Why do you think the Deep Walk one is better?
I mean, they're just like actually schools closer to Stony Brook.
There is a meaning it's capturing. Certainly these schools are geographically closest to Stony Brook. Okay. The nearest neighbor is, another one of the SUNY, universities. Okay. All of the rest of them are kind of New York. Here, Duquesne University, I believe, is in Pittsburgh. I'm not sure, and I don't know anything about it. Wellesley is an all-women's school in Boston. Okay? Illinois-Urbana is where I got my PhD. But, has no particular, modulo that, has no particular affinity for the school. I personally think Deep Walk did it, but it's fine that you have a different opinion. There's nothing wrong with having different opinions. Let's look at the second climb here. When we look at what are the nearest neighbors of Baidu, what is Baidu? It's like I think of it as the Chinese Google, okay, on some level, okay? Which one of these does a better job? Which are the nearest neighbors closer to Baidu? Does anyone have an opinion? Which one they like better?
Most of the websites.
Okay, you don't know too many of those websites, okay?
Yeah.
You think which one? You think Randeni is better, okay? And let's take a look at this thing. You're thinking to me that you liked, in fact, why do you like Randeni better? Okay, so you're saying that under Randeni you're getting search companies like. You say Free Patents Online is a search company. Okay, maybe. DuckDuckGo is a search company. Um, you know, that's what you're looking at. Okay. Are there any other ones that you like? Which one?
I don't know if that Wikimedia on different.
Wikimedia is kind of associated with Wikipedia. Okay. Now, what about deep walk companies? Does anyone feel anything about the deep walk companies? You say this is like Baidu. Very similar. Okay. Now, I don't know too much about this stuff, but I do believe that QQ is a Chinese company, isn't it? Youku, is that a Chinese company? Is 183 a Chinese company? So, Renren, I believe almost all of these are Chinese internet companies, right? So, which do you think is better? Okay, you thought Randani is better. Okay, are there other opinions? Which do you think is better? You think Deep Walk is better. Okay. Oh, and see, looking at the TV, on the television, it looks like people think Deep Walk is better. Okay, and that's good. Okay. And again, the people on TV, I'm happy if you scream out I'll even make it louder to make sure, answers to this thing. Okay, let's keep going. Chase.com. What is Chase.com? Does anyone know what Chase does? What? Banking. It's a bank. Okay. Which do people like better? Deep Walk's list or Randani's list? Okay. Deep Walk, I'm looking at this thing, I'm seeing bank, Citibank, Wells Fargo, bank. Schwab is kind of an investment company, it's sort of a bank. Discover card, money. Credit cards, money. Credit card. What do I see here? I see a bank, but I see FedEx. FedEx is a delivery company, right? I see Travelocity, that's a travel site. Okay, I see Delta, which is an airline. Okay, so which do we think is better here? Deep Walk. I think Deep Walk is better here. At least we have it. Now, what about Wikipedia? Now we have the last one is Wikipedia. Okay, what are the nearest neighbors to Wikipedia.org? Which one do we like better? Okay, I think the Deep Walk one is better. They're all kind of information sites. Time and Date is an information site. I'm sorry about that. Quora is an information site. Dig, I guess, was an information site. But this one, Wiki. Okay. Answers.com is an information site. Which do people like better? Wikipedia.org Deep Walk or Randani? Deep Walk, do you have any disagreements? Okay. So my personal belief, again, we've had some debate, more debate than when I usually show this, by the way. But I think that, actually, let's take a vote. Which one do we think is better? Who here thinks that Deep Walk was better overall? One. But maybe two. Who here thinks that, that Randani was better? So according to the vote of this 220-member class, by a score of 2-0, people think that Deep Walk was the better one. Okay? In fact, when you look at the cluster structure of these, this is the clusters. If we now take these points and project them down to 2 dimensions, what is this showing me? This is showing me parts of the web with the color of the points based on what the last domain, what the domain of it is. Is it .edu, .uk, .jp? Okay? And I think visually you can look at this in the deep walk one, I think you'll agree, has a clearer cluster structure than the RandNE one. Okay, which is, I guess, another vote that deep walk is the method that performs better. I will confess that. Okay, but what I do find, the lesson that I want you to come up with is that you can anecdotally evaluate some of these things. How well is your system working? By taking website, nodes, elements, rows where you think you know what should be closest. And, just being able to eyeball what the nearest neighbors are. If your feature-based representation is good, okay, then the nearest neighbors should make sense to you. And I find that to be a very powerful thing for making sure that your feature representations are good, making sure that, you haven't done dumb things, okay, stuff like that. Any questions about that? Okay. So what I'd like to talk about today are how you use these kind of nearest neighbor methods for classification, for eyeballing, for things like this. And the basic method, as we said, was simple. Given 2 points, you want to compute the distance between them. Now, one of the issues that you have to worry about is what property are you using? What formula or equation or measure are you using for your distance? Distances that we are used to in the world satisfy a property of things being called a metric. A distance formulation is a metric if it satisfies the following properties. That the distance between two things is always positive, right? My distance to you is not -3. It's always going to be greater than or equal to 0. The distance from me to you is 0 if and only if we're the same. The distance between Baidu and Baidu should be 0. The distance between Baidu and Google should be something, and it should be something positive. Okay? Distance metrics also have the property that they're symmetric, that the distance from me to you is the distance from you to me. Okay? And finally, they have the property of the triangle inequality, that the distance from me to you is always no bigger than the distance from me to somebody else, plus the distance of that somebody else to y. Okay? They call this the triangle inequality because it basically says the distance from x to y cannot get shorter by going through some node z. Okay? It might be that it isn't longer to go through z. If z happens to be on the direct line as the crow flies from x to y. Okay? But these are 4 properties that we have internalized about the way distances should work. And any distance function that satisfies these 4 are called a metric. And distance metrics have certain properties you can prove things about. So it's kind of a good thing if your distance function is a metric. Any questions? Yes?
If we have a graph, a weighted graph,
Yeah?
and we can not satisfy the last one, triangle inequality.
Okay, so you're saying in a weighted graph, let's say we could imagine a world where the edge from x to y had a weight of 2, or 3, let's say. The edge from x to z had a weight of 1, and the edge of the weight from y to z had a weight of 1. This is kind of what I think you're saying, right? that in weighted graphs, you're saying that distances don't naturally satisfy the triangle inequality. And that might be true. But notice that this is then a weird thing. This violates our intuitions about distances. And so if you were going to be using weights in a graph to try to use distance functions on it, recognize that this is a bad thing and not a good thing. Okay? And how might you be able to fix this problem? Sometimes if you're worried about this, what you will do is come up with a graph, take your graph G, and construct the graph G prime, where the weight of the edge xy is the length of the shortest path from x to y. Okay? So a reasonable thing to do in a graph like this might be to pre-process it. Replace every edge by the weight of the shortest path between the two of them. Okay? And then now you satisfy the triangle inequality. And now life is better. Okay? Any questions about that? So the Aubert shortest path matrix satisfies the triangle inequality. Okay? And that might be, in certain contexts, a useful thing to be able to do. Any questions? So what is not a metric? Again, sometimes things don't satisfy the triangle inequality. What's an example of a graph which does not satisfy the triangle inequality? I think in terms of the graph, you have a graph where you have the vertices are airports, and the distance between two airports is defined as the cheapest airfare from X to Y. If you've flown enough you've probably seen anomalies where the cheapest way to fly from X to Y might not be directly, but instead fly from X to Z and then from Z to Y. Okay? This is one of the reasons why it's so hard to find the cheapest airfare, is because the triangle inequality does not hold. Okay? If it held, it would be a lot easier to do it. What other measures do not satisfy the triangle inequality? Well, we've talked in here about using either the correlation coefficient or the cosine similarity. As, again, if we think of each vertex as being a point in, a d-dimensional space, the dot product, okay, of the 2 points is going to be a measure of similarity. Okay, it's cosine similarity. The thing to note here is that these go from -1 to 1. -1 to 1 is not from 0 to an infinite thing. So you can have negative similar, So the important thing is that correlation and cosine similarity measure what you call it, the distance. No. Distance functions measure how far apart they are. Correlations measure how similar they are. Okay? And so they kind of have a different scale to them. That doesn't mean that you can't ask, what are my 10 nearest neighbors in terms of correlation? Okay? But recognize that it's not a distance metric, and so weird things kind of sometimes happen. Okay? There also are kind of measures of similarity, like mutual information statistics, which are often not, they kind of are supposed to be, how much you have to transform A to get B. Often they're not symmetric, and none of these would be officially classified as metrics. Any questions? Okay. Now, the most popular distance metric that you guys certainly all grew up with was something called the Euclidean metric. What is the Euclidean metric? If we have 2 points, x and y, each of which is in d dimensions, Okay? What's the distance between x and y? We take the absolute value of the differences of y, of the ith point of dimension of x minus the ith dimension of y. We squared it, we summed it up, and we took the square root of it. This is what we are used to as the Euclidean distance. Okay? Any questions? Now, why do we use the Euclidean distance? Does anyone know why this is a distance? Okay, the function people use for distance? Well, it's certainly convention. It kind of enables the Pythagorean theorem to work. That's one thing that I guess it does. Okay? And Euclid used it. But there's other distance metrics in the world. We don't have to necessarily use the Euclidean distance. Okay? But this is a common thing. One thing to note here is that the Euclidean distance weighs every dimension the same. Okay? If every person was a point in height and weight and, let's say, a height-weight space, in principle, the distance between two people in height-weight space, okay, is going to be the sum of the differences in the height squared and the weight squared. Now notice that the default of Euclidean distance is to try to give these two dimensions equal weight. But notice that what happened if we measured weight. Let's say somebody's weight was measured in pounds. Normal weights in the United States probably go between, I'm going to say, 100 and 250 pounds. What's up with the height of people in the United States? Okay, if we measure them in inches, okay, people's height in inches probably naturally goes from about, I'll say 50 to, what's a 6-footer is, maybe about 80 inches. Notice that if we were comparing a point in height-weight space, okay, even though the Euclidean function, it does not explicitly bias against some dimensions as being equal, notice that the weight range is a range of 150, whereas the height range is a function of, only is about 30 in practice. The difference between two people in their weight, two people in our class, between the heaviest and the lightest, we probably have a weight difference of well over 100 pounds. The difference between the shortest and the tallest is probably no more than 30 inches. If we plug these things in here, if the distance is going to be more heavily weighted according to weight than height, because there's more variation there. So if we want to find nearest neighbors and things, this is a good reason why you would want to convert these numbers to z-scores first. You'd like all the different dimensions of your data point to be comparable, because if you want the influence of each dimension to be equal, you need to do that normalization, because the formula won't do it. You might conceivably do it by having some coefficient associated with normalizing it afterwards, saying certain dimensions are more important than other ones. But it's better, actually, if you, normalize each dimension first. Any questions about that? Now, the Euclidean distance, I told you, is not the only distance function in the world. Okay? Let's imagine we are in Manhattan. In Manhattan, okay, the cities are arranged in a grid. There are roads, and there are buildings, and you can't pass through buildings. What is the effective distance from this point to this point? This is the coordinate 0, 0. This looks like this is 1, 2, 3, 4, 5, 6. This is going to be 6, 0. And this, I'm going to guess 1, 2, 3, 4, 5, 6. This is 0, 6. Okay? Notice that we could talk about this as being the square root of 6 squared plus 6 squared. That would be the Euclidean distance. But the truth is that any way you walk from here to here, you're going to have to go 6 blocks to the left and 6 blocks up. The truth is this building over here, B, is 12 blocks from this square, because you can't travel in that Euclidean, along the Euclidean shortest path. You can't travel as the crow flies. So there's a generalization of Euclidean distance, which they would call an LK norm, where what we're going to do is it's going to generalize the thing by saying we're going to take the sum over all the dimensions of the absolute value of the difference of the ith dimension, raise that to the kth power, and then take the kth root of the sum. Notice before when we were talking about Euclidean distance, k was equal to 2. When k was equal to 2, we squared the differences and took the square root of the sum. Okay? On an LK norm, k does not have to be, 2. If k is equal to 1, we end up with the Manhattan distance. What happens if k equals 1? We're going to sum up the absolute difference of the coordinates. Here, 6 plus 6, k is 1, it doesn't do anything. The 1th root of it doesn't do anything. The LK distance when k is 1 is the Manhattan distance. When k is 2, it's the Euclidean distance. What is it when we let k equal to infinity? What happens as k gets larger and larger? Okay? We're summing up over d dimensions. The difference we are raising to the kth power, where k is huge. Okay? And then we're going to take the 1 over kth root of that thing. What is going to happen here? If k becomes very, very large, notice that if I have 1.1 versus 1 to the kth, as k, even though 1.1 is close to 1, when k gets bigger and bigger, it amplifies the bigger value much more than the lower values. Okay? And when you take the kth root of the power, so if k is large enough, the smaller differences melt away compared to the bigger one, and the biggest single difference dominates it. So the L infinity distance asks us which is the dimension that maximizes the largest difference. Here we have a world where this difference was 6, this difference was 6. Okay? The LK distance is going to basically be 6. Okay? The L infinity distance is going to be 6. If this block was 1 further, okay, this would be 7. Okay? Any questions? By all of these things, whatever value of k you use, it is a distance metric. It satisfies all the properties that we had before. But picking different values of k regulates whether you're worrying about what is the largest dimensional difference along one dimension, or are you talking about the total sum of the difference over many dimensions? Any questions? And picking, depending upon what k you choose, okay, will let you decide when you say which is the further point, or the equivalent, the nearer point, okay, from, let's say, the origin. Here I've got 2 points, 2, 0, and 1.5, 1.5. Which one is further from the origin? Well, it depends what the k is in your distance metric, okay? If it's k equals 1, okay, the sum of the differences between this is 2 and 3. So the further one is going to be this one, 3. For k equals 2, the Euclidean distance, this distance is going to be 2 from the origin. This turns out going to be 2.12. Again, P2 is further. But by the L infinity metric, this is the further point from the origin. Okay? So you get to choose your k when you pick a distance metric. Which one should you pick? You know, it depends kind of, I think one of the issues is whether you're talking about random noise. If you think about 2 points, okay, you know, if you have a certain amount of measurement error on each dimension, then you're probably less concerned with small differences between, the sum of a lot of small differences than you are about one big difference. So you might very well value the single dimension that they differ the most as being more important. If you have, a big potential measurement error on one dimension, okay, and you'd like to kind of ignore it, something that weighs all the dimensions equally, or little deviations equally, might be more important, okay? Any questions? So the right way to think about it is to realize that the reason why we use the Euclidean metric in the world is because we want circles to be round. Okay, what is a circle? A circle of radius r, radius 1, is the collection of points that is a distance 1 from the origin, right? According to the L2 metric, circles are round. Okay? According to the L1 metric, circles are diamond shaped, right? This is a distance, this is the point 0, 1. This is the point 1, 0. This over here is the point 1/2, 1/2. All of those sum up to be 1. For the L infinity metric, the distance is the bigger difference of the dimensions. Here, this is going to be 1, 0. This over here is going to be what? This is going to be 1, 0.99. Okay, the bigger of them is 1. This is the shape of the circle for the L infinity metric. This is L2, this is L1. I think those are pretty easy to reason out. In general, as you raise the k beyond 2, circles get more and more squarish. Okay? Any questions? Okay, so one thing to recognize is you got to pick the right, invariant, the right, right metric. The other thing to recognize about distance metrics is that our intuitions about distances in higher dimensions are very wrong. We have generally lived about in in a a 2 or 3 dimensional world. We understand distances pretty well there. Strange things happen when you get the higher dimensions. And when you take the Euclidean distance of 2 feature vectors in 1,000 dimensions, you may find it's not a very sensitive mechanism to tell the similarity of things. There are a lot of points that are going to be roughly as similar, okay, in high dimensions, okay? Often it's a good idea to do dimension reduction before you do your distance computation. Generally, we have a better intuition of dimensionality of distances in lower dimensional spaces, doing something like singular value decomposition or some other dimension reduction. If you have really high dimensional data, quite likely the nearest neighbors you get after that will be a lot more robust than the original space. Any questions? Okay. And like I say, it's important that you normalize the dimensions of the data before you try to compute a distance, okay? Because if not, the distance is going to depend more upon the dimensions with the bigger ranges than with the little ranges. Actually, if you did a singular value decomposition, the magnitude of the numbers on the low components is often larger. The more important components is often larger than that of the smaller components. The smaller components are more noisy. Those are usually smaller. Okay? Actually, if you use something like SVD, it may be that the normalization is kind of less effective or could be a problem. Any questions? So, okay, so let's say we now know how to compute the distance between 2 points. Our goal was to try to use nearest neighbor methods for classification and regression. One thing to note is that for classification, I think people have the idea that, find the label of the closest point and give me that same label. That's the idea of nearest neighbor classification. And that should make sense. Notice that we can also do regression by nearest neighbors. Suppose, let's say I know what was a regression problem. Let's say I want to know the salary that a job is going to make, a person's going to make, okay, once they get their first job. If I have records of a lot of people in the world, okay, and what their salaries were, okay, and I then did, add another query point, and I say, estimate what salary this guy is going to get. One way to solve that regression problem is find the nearest point, the record that seems most similar to it, and assign that the salary of that point. Okay? Or maybe we'll find the 3 closest points and take the average of those salaries. Okay? It should be clear that we can do regression as well as classification here. Classification was a label. Regression was to predict a number. And there are a bunch of different averaging schemes you can use here. Okay? Perhaps you average the 3 nearest neighbors or the 5 nearest neighbors. Perhaps you weigh them according to their distance. Maybe I have my 5 nearest neighbors, but one is a lot closer than the other 4. Maybe I should give extra weight on that one. But based on these kind of things, you can compute numerical estimates of things, not just labels. Any questions? Now, one parameter that's important in a nearest neighbor method to achieve some level of robustness is basically by how many different neighbors we choose to vote on, okay, for our method. The simplest nearest neighbor method gives me the label, or in the case of a regression, the numerical value of the point that was closest to me. You can get more robust measures if you're allowed to vote over multiple nearest neighbors. Okay, over the closest neighbor, over the k closest neighbors. And what value of k you use changes the decision boundary in a classification problem. Here I have our height weight data for men and women. Okay, if I assign every point in space the color of its nearest neighbor, this is the decision boundary that I get for k equals to 1. What is your reaction about that? Notice that this decision boundary isn't even connected. There is a region out here that is disconnected from that. This also looks like an island. Okay? What do we notice? Why is there all this space here that is colored, red, presumably for female in the, in the height weight space? There happened to be one unusually heavy woman who was pretty tall, okay, and there are no close neighbors to it, okay? And so this entire region over here got classified as, would get, any point in that region will be classified as woman if we set k equals 1 just because of that one example. If we have larger values of k, okay, for a classification, we can do it by voting. If k equals 3, I'm going to have 3 neighbors. I'm going to need to have, a region is going to have 2 neighbors that are men for the point to be called men, 2 neighbors that are women that are called to be called women. And as you can see, the requirement that we now have 2 out of 3, we give every point in space the label of 2 out of 3, suddenly this region all will be labeled as male again, okay? And the boundary becomes smoother. Although we still have kind of weird artifacts there, okay? Where, where, this point here, it happens that all the points in this space happen to have 2 women neighbors. It looks like that is a woman point and that is a woman point, okay? And because there's no other points near there, that region becomes labeled all as women. By the time we get to k equals 10, the boundary becomes much smoother and more sensible. So it should be clear that we still get a nonlinear boundary. It's not nearly as nonlinear as before. For a larger value of k, the decisions become more robust. On the other hand, if there are weird pockets, they will get swallowed up, in other things. This is kind of like a bias variance trade-off, okay? For larger k, we end up getting smoother surfaces. Any questions about that? How would you, if you were training a nearest neighbor classifier, what's involved in training a nearest neighbor classifier? So let's think about this. You have a set of n training examples, okay? Each one of them has a label. How would you train a nearest neighbor classifier to do well? So one thing to say is it's already trained, okay? There isn't any training, is there? Okay? Arguably, once you fix k, it's already trained, right? Now, there are some decisions you have to make, okay? You first have to decide what k is. You have to decide what your distance function is, right? You could have used Euclidean distance. You could have used something else. You could have normalized your weights differently. So there are some decisions that get made. But one of the great things about a nearest neighbor classifier is there really isn't that much training going on. What is a fair thing to do, probably the simplest thing you would want to do, is evaluate what is the accuracy for different values of k. Okay? You could imagine trying each value of k for each one of the training points. You know what the label point is. Find the k nearest neighbors to this. Take the majority label of that and decide whether each point was labeled properly or not. Okay? And that's a way that you could help set what was the right k for this. Okay? You want a boundary, you don't want too smooth a boundary. What would it be if I picked k was equal to n? Okay, what would be the nearest neighbor? What would be the decision boundary? If I have n training examples, and I demand, I guess, the n minus 1 nearest neighbors for every point, what is that going to be? You know, presumably, okay, if you have, looking at all the endpoints, if k is n equals minus 1, if you're one of the points, basically it's the same n points. Let's just set it equal to n. Let's just make it simpler. For any given point, all n points are going to be exactly this n nearest neighbors are going to be all n different points. The same set of nearest neighbors would happen from any position. So what is the nearest neighbor search space, the decision boundary? Well, whatever the majority label is, it's going to ascribe every point the majority label. Okay? So for a large enough k, it's going to get to be so robust it actually ignores the content of the data. Okay? Any questions? Now, I happen to like the nearest neighbor method a lot because it's kind of based on making decisions based on analogies. If you want a philosophical thing about nearest neighbors, we don't do that as much in computer science as many other disciplines do. In law, at least in the American legal system, what is it that you decide a case by? Typically, a case is decided by which case in the literature that somebody else decided. Which law should apply here? Well, which was the most similar case to what we have now? The circumstances were most similar. And then what did the judge decide back then? That is based on precedent, okay? And that is really an analogy. This case is like that case because blank. In medicine, what do doctors do? My doctor, I am proud to say, is about 85 years old. I go to him. He's seen a huge number of patients before. When I go in, he's thinking, okay, you've got this 60-year-old guy and he's sneezing and he's coughing and he's doing this. I saw somebody like that 10 years ago. And when I gave him this drug, everything got better. Okay? A lot of the thinking that doctors do is based on have I seen similar patients and what did I do to make them survive? When it comes to real estate pricing, if you talk to a real estate agent and you say, what will my house sell for? They will say, well, what are the comps? What are the houses that are in my neighborhood that look most similar to mine? And what did they sell for? Many parts of the world use this kind of analogical reasoning, and I think that's actually a good thing to think in terms of, and that's one of the reasons I like the nearest neighbor methods. Any questions? And I just love looking at nearest neighbor things. This is me personally. Again, I know all of you I've been trying to convert to become baseball fans over this year. I know I probably have not succeeded, okay, with anyone. But, thing that's interesting is when you look at the records for a particular player, what other players had most similar records? So Mike Trout is a famous good young baseball player these days. And people wonder, how is he going to compare over his lifetime over to other players? Well, when you look at his statistics compared to what he's achieved over over his first 10 years of being a baseball player, you'll see that the players that were most similar to him were all some of the biggest stars of all time. Okay? The stars, if they have a star next to their name, that meant that they were a Hall of Famer, which is a measure of them being among the best ever. So similar players to him, based on his record so far, okay, at the age that he was, were all unbelievably great players. If you look at people who had lifetime records like he does, these guys were not quite as good players. Why is that? This guy's still got 10 years of playing life left in him, and he has the ability to achieve a lot more, okay? But looking at who the most similar players is, or if you're doing something about movies, it's always interesting. Oh, I like this movie. What movies are most similar? Okay, I think nearest neighbors are a good thing. Any questions about that? Any questions about how nearest neighbors work or why I like them? So what's good about nearest neighbors? Again, if you want to build a nearest neighbor classifier, you don't have to do any training. That's good. But what's bad about nearest neighbor methods? Well, suppose I have a training set, okay, of endpoints, each of which is in d dimensions. And I now have a new query point, Q, which is obviously also in d dimensions. Okay? How much time does it take? How do I find the nearest neighbor to Q? Okay? In my data set. The simplest algorithm, the one that seems most obvious, is I compute the distance of me to every one of the other endpoints. Each distance computation takes order d time. Okay, it obviously takes longer to compare points in 100 dimensions for similarity than for points in 2 dimensions. It takes order n times d time to find the nearest neighbor to a query point if you've got n points in d dimensions as your data set. Okay? So if you have a large, what I'm going to call training set, we're not really using it as training, we're using it as parameters. Okay, it becomes expensive to try to find the nearest neighbor. Okay, and this is kind of one of the, if you say what is a big downside of the nearest neighbor method. For large data sets, okay, the search time gets to be hard. And that's something that now motivates us looking at algorithms for finding the nearest neighbor of points efficiently. Any questions? So how can we find the nearest neighbors better? Well, if you took a course in computational geometry, okay, there are a couple of techniques for finding nearest neighbors efficiently that that you might hear about that work reasonably well in low dimensions. Okay, what is the most famous one? Most famous one is something called a Voronoi diagram. What is a Voronoi diagram? We would like it if we had points here in 2 dimensions. What would be a good way to find what the nearest neighbor of a point is? If I plot my pen down here, the Voronoi diagram carves space up into regions. And all the points in one region have the same nearest neighbor. Okay? Let's think about it. If I only had 2 points, if I wanted to carve the plane up and I only had 2 points X and Y, how would I carve space up, okay, into regions such that all the points in one region are closest to X and all the points are in the other region are closest to Y? Yeah, how do you do it? Middle distance, and I believe that is the perpendicular bisector, is what we learned when you were taking it in geometry, right? You said that there was a, what you call it, you could find what is the slope of the line here. The perpendicular line is the one that's against it. That was 1 over the slope. The slope of that was 1 over the original slope. The perpendicular bisector, okay, is the line that kind of is in the middle of these points. Every point on this line is equidistant to X and to Y, okay? If so, that means that everything on this side is closer to X and everything on this side is closer to Y. By taking the perpendicular bisectors between all points and properly processing it, you get a Voronoi diagram. Notice that the edge of the Voronoi diagram is part of the perpendicular bisector between those 2 points. The Voronoi diagram carves space into the, into regions such that all the points in a region have the same nearest neighbor in the training set. What's good about that? Once I have my Voronoi diagram, the problem of finding the nearest neighbor to a point reduces to simply finding what is the cell that contained that point. It reduces the problem of nearest neighbor search to a problem called point location. And in low dimensions, ideally 2 dimensions, there are great algorithms for finding, you can build a Voronoi diagram in something like n log n time, and you can search it in something like log n time, okay? So if you've got 2 dimensions, Voronoi diagrams are great things. If you've got data in more than 2 dimensions, by the time you get beyond 3 or 4 or something like that, Voronoi diagrams become very, very complicated. Okay? It's part of the thing that life in higher dimensions is different than life in low dimensions. Any questions? So Voronoi diagrams only work well in low dimensions. But there are other data structures that are good for modest numbers of dimensions. Okay? Data structures that build kind of hierarchical trees on the thing. Have a plane that goes through this. Are you on this side or that side? If you're on this side, go ahead and look now here. Are you on this side or that side? KD trees, okay? Kind of divide space into regions by cutting things with planes, such that it balances the, the size of the number of points on each side of the plane, okay? Searching through one of these trees, again, has something like logarithmic height. And ultimately, the cell that you come down to is probably going to be pretty close to the optimal, is pretty close to the nearest neighbor of your query point, okay? So these data structures are helpful. They work well in modest numbers of dimensions, maybe up to 20 dimensions or 30 dimensions or something like that, okay? There's something for even higher dimensions called ball trees, okay? That instead of carving it down by lines, kind of use circles or spheres to kind of do this decomposition. Bottom line is, if you really have to find the exact nearest neighbor, it's going to reduce to doing linear search in high dimensions. But finding a close nearest neighbor, okay, can typically be done using these data structures relatively efficiently. Any questions about KD trees or Vonar diagrams? Yes.
Shouldn't we use a school function and then we can use a binary search to find the nearest?
Okay, so you're saying that if you have a score function on these points, let's say you wanted to find the nearest baseball player to somebody. And let's say that you had a single statistic of, let's say, how valuable a player is, a scoring function. You've now really reduced every player down to one dimension, okay? And now in one dimension, is nearest neighbor search easy? Well, nearest neighbor search reduces to binary search in one dimension, right? If you have the values sorted, to find the nearest neighbor to a point Q, that's binary search. So that is one thing you can do, okay, if you have a scoring function that really means two similar things, two things that have similar values, okay, can be are identical things. Okay, so that's fine if your scoring function is so good that when two things have similar value, they really are similar records. Now that's not necessarily true, okay? I can imagine, let's say that the value we put on you is going to be, what your salary is going to be or your lifetime earnings, okay? You're going to have a good lifetime earning as a computer science person, okay? You can imagine somebody else is a very, very good insurance salesman who ends up earning about as much money as you. You could imagine that if they earned the exact same money as you, are they really your nearest neighbor? Okay, you differ in a lot of different properties, right? So the problem is, if you reduce everything to one dimension, you might very well conflate two things that are quite different, but look the same in that absolute thing. Okay, does that mean that that's a bad thing to do? Not necessarily. Okay, but recognize that that's what the danger is. Okay, that's why when we did something like singular value decomposition, we took something from a large number of dimensions and reduced it to a small, but typically not one dimension. We could have just used the first dimension, the first singular value, as a one-dimensional representation of everything. Typically, to avoid warping the space too much, you need a bunch of dimensions, okay? There's some kind of theorem that's you need to know. If you have d-dimensional data, if you've got something like log n dimensions, if log n squared, okay, if you originally start out with n points in d dimensions, if you convert them to n points in log n squared dimensions, you probably haven't lost anything really about the shape. So if d is very large relative to log n, there's always a lot of room to do that compression. But getting down to one, the space is going to be a lot different. Any other questions? Okay. What other data structures are there to tell if nearby points? Grid files, you can kind of imagine setting up a grid on each dimension and kind of hash points to, every point would then sit in a particular grid cell. If I want to find the nearest value to this thing, maybe I will just look among the points that are in my grid cell. So there are these bucketing based on grids. This gives you a way to identify close points quickly. The trouble is, maybe your point is going to be in an empty cell. Okay? Maybe the nearest neighbor, if I put a point here, my nearest neighbor might be this instead of something in my cell. Okay? But that's another way to speed up search. The last method I'd like to talk about for finding nearest neighbors quickly is a new method that's actually quite interesting, and so I do want to talk about this. a technique called locality-sensitive hashing. Hashing, if you took computer science, you took a data structures class, you probably learned about hashing. What was the idea of hashing? Suppose I have a d-dimensional vector. Hashing is I will reduce it to a single one-dimensional value by, computing some kind of arithmetic function on these points and dividing it by the range. A hash function, okay, is something that's used in hash tables and things like that. It takes as input the point and it comes out with a single number, okay? And these numbers can be used to define buckets. Two things that got the same number, hash value, would go into the same bucket. Normal hash functions, the ones that you studied when you took data structures classes, does not usually respect distances. If I have two very, very similar values, you could imagine hashing the point 1, 1 and the point 1, 2. These 2 points are close to each other. If you convert them to hash numbers, you'd like it to be the case that this got 76, this got 673. You'd like it that different values got similar values. Different points that were close to each other got similar values, but much different points. 5, 5 went to 1024 or something bad. But normal hash functions don't have that property. Locality-sensitive hashing is a technique that takes points, or equivalently vectors, A and B, computes a hash value of it, a number, with the property that these numbers should be close to each other if A is near B. When you had the score function, you said, oh, give me a score function. And similar points will lie near each other. This was what you were kind of wanting to do. Okay? But the score function itself doesn't necessarily, as you define a normal scoring function, very different records might collapse very similarly to each other. Okay? Locality-sensitive hashing is a technique that tries to ascribe a number to each record, such that nearby points get the same number. What is an example of how locality-sensitive hashing works? The simplest thing is, let's say that all the points were on a sphere. So they were like records. They were like vectors. Suppose I pick a first random line, L, and I pass it through the center of the sphere. What is interesting about this line? If you say what is the closest point to this point, it is if this is the right side of L and this is the left side of L. For most of the points on our in our data, the nearest neighbor on the sphere is probably going to lie on the same side of this line as I am. That's not always true. If you look at this particular line, the nearest neighbor of that point, unfortunately, is on the wrong side of L. Okay? But generally speaking, for most of the points, except for this one, and probably this one and this one, okay, the nearest neighbor to each point lies on the same side as the point itself, okay, almost certainly, okay, for all the points. So what is the idea? We can draw a random vector L, and every point can then get labeled either 0 if it's on the left side, or 1 if it's on the right side. I can then come up with another random vector, L2, and again label all the points. Are they on the left side or the right side? Now, there's going to be 0 points and 1 point. These points are all going to have the code right, left. These points are all going to have the code left, left. These points are all going to have the code 1, 1. These codes are going to all have the code 0, 1. Does everybody kind of see what we're doing? By adding another vector, each time we add a random plane, we're adding 1 bit to our hash code. The points that are near to us are going to likely have the same hash code, okay? And by using these hash codes, interpreting them as numbers, okay, the left to right patterns for these D bits will determine a hash code that takes all the dimensions into account, okay, and likely similar points get similar hash codes. This then puts the points into buckets. If you now want to find the nearest neighbor to this point, what do? I compute for my query point, I compute the code for my query point, and my nearest neighbors would be points that are in the appropriate, have the same code. This is the idea of locality sensitive hashing. And this is a very effective way of finding close neighbors quickly. Any questions about that? Okay. If not, any questions? Okay, if not, thanks for your attention. Good luck finishing your project progress report, and we can talk about it in my office if you wish. Okay, thank you very much.